Okay, so now that we had an overview about intermolecular forces and their strengths, we now need to be able to do a few examples looking at the intermolecular forces present in various molecules. And again, it comes back to the molecular polarity. So in order to be able to determine molecular polarity, you have to be able to draw Lewis structures and look at the 3D shape. Now, our first example here is a little bit of an oddball in that you really don't need to draw any Lewis structure in order to determine the molecular polarity. Because we have helium and nothing else is present, we know that this is a non-polar molecule. It's not bonded to anything else. So as a result, we can consider it to be non-polar. And since what we've just learned about intermolecular forces, we know that all non-polar molecules have London dispersion forces. And that is the only intermolecular force that is present. So, since we only have London dispersion forces present within this molecule, we know that it has to be the strongest. Now, if we move on to a slightly more difficult one, we look at N2. We need to be able to determine the intermolecular forces present. So we have to look at this one and say, well, what is its molecular polarity? And the only way that we're going to be able to do this is to generate a Lewis structure and also the 3D model. So if we draw the Lewis structure for N2, we know that we have to tally the valence electrons. We know that for nitrogen, there are 2 of them, and nitrogen is in group 5. So we know that when we are done with our structure, we need to have 10 valence electrons. So with this particular molecule, we need to determine which one is our central atom. Now, because we only have 2 atoms, it's really not as important that you pick which one is the central one. So I have 2 nitrogens. Pick one that you're going to deem the central atom. So I will pick the one on the left, and I will draw a single bond from my central to my terminal. Had you done it the other way, you'd get the exact same answer. So I know the steps for a Lewis structure. I know I need to give my terminal atom an octet, since nitrogen is not an exception to the octet rule. I know I need to draw 6 more around this nitrogen. And then I look, how many of the valence electrons out of the 10 have I drawn? And I've drawn 8. So I know I have 2 left over, and I place them on the central atom as a lone pair. Now, I've used all 10 of my dots. I have to check, does everything have an octet? And what I see is that this nitrogen has an octet, but this one does not have 8. So if you'll recall from Lewis structures, you know that when you have something where it doesn't have an octet, but you've used all of your valence electrons, meaning you have too few electrons, you know you have to form multiple bonds. So if we take a lone pair and we form a multiple bond, we now have a double bond between the nitrogen. And we look and we see, yes, we have indeed still used 10 of our valence electrons, but our nitrogen still does not have an octet. So again, we form a multiple bond. So we form a multiple bond, and we now have a triple bond between both of our nitrogens. So we look, have we used all 10 of our valence electrons? Yes, we have. Does everything have an octet? Yes, both nitrogens have 8 surrounding it. So we know that this is our Lewis structure. Now, in terms of determining molecular polarity, you know you have to look and say, okay, first thing, what type of bond is present? You know that when you have polar bonds, you can either have a polar molecule or a non-polar molecule. But also, if you recall, when we have non-polar bonds, meaning the electrons are the electronegativity between the 2 atoms in the bond, there's no significant difference, meaning we have non-polar molecule. So if we look at this particular Lewis structure here, we see that we have a nitrogen bound to a nitrogen. So there is no difference in electronegativity, meaning the difference in electronegativity is equal to 0 because Both nitrogens have the exact same ability to attract electrons to themselves. So, what this means is that this molecule contains nonpolar bonds. Therefore, this is a nonpolar molecule. Therefore, you know that since we have a nonpolar molecule, the only intermolecular forces present are London dispersion forces, and since they are the only ones present, you know that they have to be the strongest.